apoyo. Gracias, muchas gracias. So I feel like Don Quixote. I don't know if anybody, has anybody ever looked at my web page, because I have a little Don Quixote drawing there, because sometimes I feel like I'm chasing windmills. But anyway, so we had a little historical introduction, plus some other stuff, and now I want to show you what I think are the most painfully important observations we can make of the sun in regard to it as a magnetized, rotating body that's radiating energy into space, as an example of a really high magnetic Reynolds number system. And so there are so many papers written on magnetism on the sun that you could spend the rest of your life reading them, I'm sure. What I'm going to try and do is pick out what, from my perspective, simple physical perspective, namely an MHD perspective, what are the most important observational facts that we have that may lead us to accept certain theoretical ideas or reject them. And if you remember, the best thing we can possibly do in science is to actually have the ability to reject something. Otherwise, it's not science. It's a pseudoscience. So the idea here is to show you the most important, what I consider to be the most important observational facts about the sun that we know about its magnetic field. The first one is one espoused by Gene Parker many decades ago, and he continues to talk about it. He's a grand old statesman of the latter half of the 20th century, solar physics in America. And he still doesn't know why the sun is obliged to form a spot. Again, we're used to looking at the sun and seeing these things, so we accept them for what they are. But unlike, for instance, a lake formed in a piece of land in Spain, unlike a volcano in Teide, a few miles away from here, where we have a basic physical understanding as to where those things come from. The basic energy source is known. The basic stresses in the system are known. The forcings of this thing are known. You know, the weather system is driven by radiation from the sun, rotation of the earth, Coriolis forces, clouds come and go as a result of various processes, chemical, physical, that we know about. What we don't know is why the sun is obliged to show us its magnetic field in this particular form. That's really strange. So please don't forget that. We don't understand why the sun forms sunspots. Now, in a little bit more detail, again, going through the history here, as long ago as almost a century now, Hale and these guys realized, after the first observations were made in 1908, where they looked at the Zeeman effect in lines, and we'll get to that later on today, they looked at polarized light. I mean, many of you will be familiar with this. I talked to one or two of you about this. And if you look at the circular polarization, and this will become familiar, I'm just going to use the words now, left minus right circularly polarized light, which Hale did in 1908, he realized that in the northern hemisphere, the polarity was, a leader was in the negative polarity, and the follower was in the positive polarity. This is typically what we look at when we look at the sun with the naked eye. In case of those of you that are not familiar with the coordinate system here, the sun will present some angle of its rotation axis to us from any given observing vantage on the Earth. From the northern hemisphere in the Earth, we will say, when we're looking up, that's the north, that's the south. And the sun actually the sun is spinning in this direction, so things rise in the east, which is plotted on the left, and set in the west. So it looks the opposite of the Earth. But it's because of the sense of rotation of the sun's rotating body. So here's a leader, here's a follower. The sun's rotating in this direction, going into the board that way and out of the board this way. Finally, by 1919, totally unexpectedly, sunspots started to appear of a reverse polarity. So this paper was first published. This is the discovery paper. So what is this? This is evidence that not only are the spots formed in compressed regions, as was known in 1908, of magnetism. This is supposed to be what they call a penumbra. We won't worry too much about that, but here's the compressed region here. And of course, because there's no monopoles, there has to be, this flux has to go somewhere, and in this case it goes back to the sun and returns in a follower spot here. Normally these are much more tightly condensed spatially than the followers for some reason, and these are more spread out. But look at this. This has changed in 11 years. It wasn't until the 1950s that these kind of measurements were made stable enough so that one could observe outside of sunspots and actually see that just not the sunspot field had reversed from in 11 years, but that the dipole had entirely reversed. And the dipole doesn't reverse at the same time. It reverses out of phase with the sunspot reversals. Okay. So what is this? This is evidence for a well-organized, large-scale magnetic field in the solar interior which changes polarity every 11 years. It's like having some snake or organism living underneath the sun that pops his head up, and this serpent comes up one way around after 11 years, and then comes around, it's facing the other way 11 years later. Another thing that happens is, again, Joy is one of the authors with Hale, is that there is a preferred kind of tilt that happens to these things. It's not random. There is a follower spot and as well as a leader spot. That means that, and they're organized, but they're slightly tilted as well. So not only is the polarity fixed for one hemisphere, almost always, there are exceptions, but at the 90-odd% level, you know, most of the spots have the right polarity in a given hemisphere. And by the way, the polarity is reversed in the southern hemisphere, in the other hemisphere. Not only that, but it's also slightly tilted. And the further the spots appear from the equator, the more tilted they are. So as you come down towards the equator, there's less tilt. You'll realize if you've been on one of those, what I call a roundabout, one of those things that children like to go on, but make people like me feel very sick when you get on them now, is at the fairground. And so you get on this thing and you try and walk, as the thing's going around, and you feel this bizarre feeling that you're going to fall. This is the Coriolis force. You're on a rotating frame. You're trying to go in a straight line, but the friction's pulling you this way. You experience some twist, etc., etc. So this is evidence that something in the interior of the sun is emerging. It's probably subject to, well, it's certainly got to be subject to a Coriolis force because it's a rotating thing. And the likelihood is that when we see something as obvious as this, and again, this is statistically a phenomenon, not a deterministic thing, that the tilt is bigger towards the pole than it is down here. Okay. The reason I say statistically is because of this thing here, and turbulence. And of course, Fausto mentioned the importance of turbulence earlier. Turbulence is not an understood thing. It's defeated, many decades of people's lives in coming to an accessible solution. The reason being it's basically nonlinear. Even the simple Navier-Stokes equation, which can be written down, etc., is not subject to meaningful interpretation because of the nonlinear term of the advection term. It's as simple as that. And if we imagine this being a place where the magnetic field on the sun is very strong for some reason, this is a place, therefore, where it's not very strong. This looks hydrodynamic. This looks like our boiling pot of oil. So this is just the very most surface layer of the turbulence that we're seeing here. It has a characteristic scale of a couple of megameters, 2 million meters. Solar physicists use megameters because it makes them feel important, like Superman or megameter or something. So 2,000 kilometers. And so, this is about the size of the United States, these blobs here, or Australia. And but these are the scale they are because of the nature of the release of energy by sudden release of energy at the surface by this free streaming of photons out into space. That cools the plasma, makes the plasma not have the plasma cools sufficiently that it becomes dense because there's no temperature pressure gradient to hold the thing up, and it starts to collapse. That drops down, so you get these convective eddies. And these are the very shallow ones at the very surface. But this turbulence is known to extend very deep down because we understand the thermodynamics of the physics of the interior of the sun well enough to say the interior, the transport is done by radiation. As soon as you get to about a 70% level, the radiation can no longer sustain that flux of energy, and something else has got to happen. That something else is fluid motion. So the enthalpy flux that takes over, you get this motion of fluids. The moment you get this motion of fluids, you're going to enter a turbulent state with those kind of Reynolds numbers that you have inside the sun. Okay. So let's look at, remember, we're looking at the most painful things we can to try and constrain what we think might be going on in the sun. The most obvious thing we can do is go back to the time of Galileo in here and ask the question, what are the sunspots doing? 1977, a chap called Jack Eddy published a paper entitled The Maunder Minimum, in which he pointed out that there was a period here in which there's very little magnetic activity that was obvious on the sun, both as a result of the storms coming and affecting the Earth and in the form of sunspots. Let's look at this a little bit more detail. Everybody knows who that is, right? The English people should know who this is. Come on, guys, speak up. Not you. Pardon? Sir Isaac himself, yes. Sir Isaac. So this poor old Isaac Newton, if you look at it like this, one way to remember the Maunder Minimum is that the poor Isaac Newton lived all the way through it. This happened to coincide with something called the Little Ice Age. The statistics on that have been suggestive, and in fact Eddy in his paper suggested there was a relationship between sunspots and climate. Current models suggest that there isn't enough variation in the sunspots unless there's some leveraging of the high energy radiation or something else going on. There's simply not enough variation in the solar magnetic variation in its radiance of the Earth to account for climate changes like this. And in fact, there are things like volcanoes and stuff. The Earth is a pretty noisy system, right? I mean, things like volcanoes go off, people invent cars, various things happen to generate noise in this system, and it's not at all clear how to interpret that. But anyway, that's a good way to remember the Maunder Minimum. What this tells us is that there are two things I take from this plot personally. One is, look how goddamn regular the sun is. It's like a heartbeat. If I had a heartbeat like that, I would be damned healthy for a long time, except I wouldn't do too well during the Maunder Minimum, right? That would be pretty bad. But this is remarkable. Here we have a rotating body with all this turbulence in it, and it's going dong, ki-dong, 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 ki-dong. Who could have thought of that? It's a bizarre situation. That's totally unexpected. Furthermore, there are periods of, maybe on the order of a century or so, where this is modulated. So the sun seems to remember something on a time scale of about a century or so. Maybe. That would be one way. If I showed you this and didn't tell you what it was, if I said it was a bunch of river flow measurements outside Bozeman, Montana, which I was looking at this last year when I was teaching there because I was interested in fly fishing. And when the river flow is very high, the trout can't see the flies, so you don't catch them, right? Well, I didn't catch them anyway. But, you might have come up with a suggestion that, in this period here, there was a lot of water flying down. So you have some picture in your mind as to what was going on. Here we have no 0th order picture to compare this with. These are the data that a dynamo model of the sun must be able to at least account for statistically. But furthermore, there are phase relationships here. In other words, it wasn't dark here and then, it was dark here and it's dark here and dark all the time for this period. And this lag is knowledge. The sun seems to remember something on this time scale. So, by the way, the width of the photograph is the lifespan. I forgot to mention that. Okay, this is perhaps getting a little bit harder. Does anybody know who that is? James Clerk Maxwell. Oscar Wilde could be, yeah, actually. It looks a bit like him, doesn't it? Yeah. I went to the same college as Oscar Wilde and got drunk in the Oscar Wilde rooms on many occasions. This does look like Oscar Wilde, and it's James Clerk Maxwell. He didn't live too long, poor guy. I think he deserved the credit for Maxwell's equations in getting one term out of 4 equations in. That was sufficient for me. Okay, anybody know who that is? It's a Nobel Prize winner. Hannes Alfvén. I don't think Fausto mentioned Alfvén at all, did he? Did Fausto mention Alfvén this morning? He did? Very good for him. So Alfvén, who looks very pleased with himself here, is the originator of magnetohydrodynamics. They were his concepts, Alfvén's theorem. Okay, the whole business of the coupled fluid to the magnetic field is due to him. He actually came not to believe it in later years himself, but I think he was wrong in not believing that. It depends on the question you're asking as to whether you believe MHD is applicable or not. Okay, to some degree. This guy is probably not known to many of you here, but his name has arisen before. This may give you a clue. This modest-looking solar cycle here has a star on it, and that's 1859. That's Carrington. Yeah. So, in 1859, he's drawing pictures of the sun and counting sunspots, and amongst those was this one that went bang and had a huge influence on the Earth environment. The thing I find amazing here is, if I hadn't shown you that, which one of those cycles would you pick to have the strongest magnetic effect in history? Well, no. Maybe 1955, right? Yeah, that's it. That's a good place to start. Lots of sunspots. It's going to go bang. So what we really have here is, in the same way that Fausto is amazed by the fact that MHD systems with very high Reynolds numbers nevertheless arrange themselves to dissipate their magnetic fields very quickly somehow. That's a sort of theoretical notion that's difficult to grasp. I find it difficult to grasp that we have such regularity in amongst such chaos here. I mean, this is not really chaotic behavior. Well, we'll look at some longer timescales in a minute which show more of that. But somehow the clock, it's not a perfect clock. It's a pretty damn good clock by most, if you're an animal that lived for 1,000 years or 10,000 years, you could set your clock by looking at the sun, I think, pretty well, except during the morning minimum. And furthermore, there's another aspect of this, which is related to my comment about whether it's fair to our scientists to predict things or not in this kind of nonlinear system. And that is that when you're asking about typical conditions on an object like the sun, what is the typical field strength of a sunspot? 2×10⁻³ Gauss, maybe, at the core of a sunspot, is an answer I could give you, plus or minus a few hundred Gauss. And I would say 90% of the distribution would be in there. But then I'm looking at the core of a distribution. So I'm looking at the tail of a distribution by asking the question, what is the chance of the most extreme event ever happening? And you want me to give you an answer for that one. That's got a lot more uncertainty associated with it, which is why I'm pessimistic about predicting things on the sun. Okay. One of the nice things is that the Earth is a detector of the sun. Yeah. Sure. Yeah. You're right. There is an active research area involving the recalibration of this number, both the yearly average sunspot and the monthly averages and the daily averages, etc. And there is a big difference between what certain people calculate. But what I think is not up for debate, for instance, is whether, for instance, these two, if an observer at one observatory were observing sunspots and then they changed observers, well, who decides what a sunspot group is and how many things there are? This is not an easy thing to do, actually. So this and that might be something that you would debate whether they're very different or not. However, the fact that this is so low and yet had the strongest recorded flare in history is not under debate. So it's a question of degree. But you're exactly right. There is an active research group pursuing that right now, and they've had 4 meetings so far recently. So again, what could be more boring than counting spots? How many people are going to go into a field and count the spots on the cows? It might be interesting for something biologically, genetically, right? It could be really, really fascinating. It could provide a solution for cancer or something in the end. You never know that. But just because something looks attractive and is seductive because we get all these gamma rays and X-rays and pulsars and magnetars and Mars bars and you name it coming out of this thing, doesn't mean it's good science. There's a certain amount of boring stuff that one has to do as a graduate student and as a postdoc and as a scientist to really get the results you want. I'm not telling you anything you don't know. Let me show you another remarkable thing here. The Earth is a detector of the sun. In fact, one of the most fascinating things I learned fairly early on when I went into solar physics was that we knew there was a lot of ultraviolet emission from the sun before we could observe it. Does anybody want to guess why that is? It's in the 20th century, radio communications are affected by the ionosphere. What is the source of the ions in the ionosphere? It's the ultraviolet light from the sun. In fact, a paper was written in 1948 which shows that predicts a spectrum of the sun which looks pretty much like what you measure these days before it had ever been observed on the basis of the behavior of the ionosphere. So the Earth is a detector of the sun in the same way as any other object in the solar system will be. In a rather less direct way, we have records in these things called neutron monitors, in which the big heliosphere, which engulfs, you've all heard of the Voyager missions, right? Launched way before any of you were born, 1977. England had only recently won the World Cup in 1966. It was all great and wonderful. No, the Voyagers were launched earlier than that, early 70s, I believe. Voyager just went through the termination shock in the solar wind, now into interstellar medium. In between that, in the whole sphere of influence of the sun, the heliosphere, when the magnetism of the sun is changing its sign every 11 years, the little cosmic rays coming in feel these field lines and they get dragged around them. The little cosmic rays then come in either from the poles or from the equator and lead to an asymmetry which even if you didn't know anything about, even if we were clouded out, you could make this measurement on the ground and you would figure out that this is a period when the magnetic field of the sun is pointing north. This is a period pointing south, north. These are pointy, these are flat. These are pointy, these are flat. And they alternate in time. The reason for that asymmetry is because cosmic rays have only one charge. They're positive charges. So the drifts, the particle drifts coming into the heliosphere are different according to whether they approach from the equator or from the pole and dependent on the sign of the magnetic field. I expected this to be symmetric. I didn't understand this at first. If we had negatively charged cosmic rays, this would be symmetric. If we had, it's an amazing thing. Anyway, this shows you that they're correlated. At a time when the sunspots numbers are very big, the cosmic ray intensity is very low. In other words, the magnetic field shields us from the cosmic rays. This is what you want. If any of you want to be an astronaut and go to Mars, which I wouldn't recommend, but if you wanted to, you're going to have to be shielded. And you're going to have 10 Tesla fields at least, because these guys are going to get you. And if these guys don't, the sun's own flare particles are going to get you. And a pair of lead-lined trousers aren't going to be sufficient. You need a sort of meter of lead or something to protect yourself. I don't know what it is, but anyway. What's going on? Well, how does this record get stamped into the Earth? Well, we have the galactic cosmic ray radiation. It comes in, it's modulated by the sun. So already at this point, a signal is in there associated with the sunspots and with the reversal of the global field. It impacts the nuclei and then gets deposited out in the atmosphere. It then, biological processes, then in tree rings, it can contain an imprint through these various kinds of isotopes. These have a time scale associated with them for decay, which is commensurate with being able to resolve things in time. So I don't know what the details are, but I find this absolutely fascinating. The fact that, you know, the sun's magnetic field does this stuff, and you can see it in the flipping tree rings. I mean, this is real physics on the ground. So we can reconstruct much longer in time. And, okay, this is an educated guess, and it's filtered. We don't resolve every second all the way back in time to the year minus 7,000, of course. But nevertheless, it's a data set, a time series of data, which with the ice cores and the tree rings shows us quite a lot of noise, but nevertheless contains stuff which is known to be a signal from the sun. We also see signals from the Earth. The Earth's own magnetosphere changes. On timescales of 100,000 years, the Earth's magnetic field actually flips, as we heard. But you can decompose these things. Here is a Fourier spectrum of the sun. And this is in years. So normally, when you take a Fourier spectrum of something that looks kind of chaotic, you end up with a very large low-frequency power, and that's what we're seeing here, just a sort of first-order slope to this thing. But there are various periods that actually pop up, and they pop up above the noise. Again, the sun's 11-year cycle is not alone. There are other cycles in here as well, apparently. Now, you can say, are these chaotic? Are they real? And only time will tell. But nevertheless, what we have here, the evidence of the 11-year solar cycle, and later with stars, which also show, by the way, cycles between, say, 2 and as long as we can measure. It's the same order of magnitude as the sun. There's something fishy going on here. So this is a really big, strong clue as to something interesting going on inside the sun, which is also accompanied by similar-looking stars. I just pulled this one out. I actually changed my lecture a little bit on the basis of what Fausto was going to say he was talking about tomorrow. So I hope this is all making some sense here. But I didn't initially want to show this, but it's important, I think, to realize that the magnetism of the sun does some funny stuff to the radiation we receive. And what it does is the sunspots poke through very strong magnetic fields. The stresses in that magnetic fields are stronger than the neighboring environment. So it suppresses convection. So the heat transport is suppressed. Therefore, that part of the atmosphere is not heated much from below. Therefore, they're dark. On the other hand, the regions around the sunspots tend to be brighter in certain wavelengths. If you look towards the blue, if you look in the red side, you have something that depends on the linear part of the Rayleigh of the black body spectrum. It's hard to see temperature differences. If you go way to the blue, you have e to the minus h nu over kt helping you see little changes in T, and that's what you're looking at here. And so what we see here is associated with the dark cores of the sunspots. We see something which, you know, rather romantically are called plage, French word for beaches. But they're just bright regions of disrupted magnetic field that is either actively peeling off the regions of the sun, or it's of emerged flux of the surface and being dragged around by the turbulent granulation, eaten away at the edges by the turbulence, or it's emerging flux already in a turbulent state. Okay? And we don't, I think, yet know what the answer to that question is. It's an important one, but probably a mixture of both. But what I want to show you here is we have a couple of plots here. This shows you the variation in the total irradiance of the Earth. The irradiance is just the total energy received from an object outside you. So it's not the same as the luminosity of the sun, because we don't actually know how bright the sun would look if we were to observe it from the poles. If we assume it's isotropic, this would also be related to the actual luminosity, the sheer radiative power of the sun. But you can't interpret this as variations in the power of the sun directly, necessarily, without that assumption. And what it shows you is that, what I'm trying to show you is that the amplitude is on the order of 1 part in 1,000 or so, the RMS amplitude of the measured radiance at the Earth, irradiance from the sun. This is something you can measure in stars. That's what Kepler has been measuring, actually much more accurately than that. This is actually a hard measurement to make. Believe it or not, the sun is harder to measure than the stars in some sense. When you measure stars, you typically measure a target, and you have 3 stars around it that you choose to compare them with, and you use statistics to beat down any variations of those 3 stars, and you reject other stars that are clearly variable. The point is, you have a very nice set of standard stars whose relationship in space is separate, very different. Some of them are along the line of sight. They don't belong in the same cluster. What it means is that you have a very good differential measurement. We don't have such a thing for the sun. We've actually got to measure the power, and we've got to calibrate it. And this is a combination of 1, 2, 3 different instruments, and the offsets are 10 times larger than the variations we're seeing there. So the absolute calibration of these things is not known well enough, but the statistical cross-correlation between them is used to generate a plot, and we believe this is currently typical of the amplitude of the variation. So the sun's magnetic field somehow is blocking 0.1% of the light as the solar cycle progresses and wanes. So there's if we know that the luminosity of the star itself is constant, so what it must be doing is storing energy in the interior for a while and then letting it go again. So this is almost a quasi-stationary state. It's not a completely stationary state. Further, the question is, spectrally, as sunspots cross the disk, in the red, the sun appears a little bit darker. In the blue, it appears brighter, because these dominate in the blue and those dominate in the red. And in the ultraviolet is just a more extreme example. So that during solar maximum, things like X-rays and ultraviolet are really, really strong, by a factor of 10 or something than the average. Whereas the red light would be a little bit dimmer. Not all stars are like that. Stars can differ. Okay, more basic observational facts for us to lay at the feet of the theorists. We all know that this is called a butterfly diagram as a result of a chap called Maunder, and actually a Mrs. Maunder as well, who was the one, actually, I think, that drew most of the plots that we have. We have one of the original butterfly diagrams of Maunder in our observatory on the wall back home in the United States. So what are we looking at here? We're looking at, again, sunspot number versus time, but also we're looking at what the daily area is in equal latitude strips. So this is an attempt to take out the projection effects. And we're seeing that as time goes on, at the beginning of the solar cycle, there are no spots just before the beginning. And as it starts, they appear at high latitude, and then they kind of migrate towards the equator. Okay, so this is the well-known butterfly diagram. And you see various things in very strong cycles. Remember, we mentioned 1955. You see a large sunspot area in the southern hemisphere. So this, again, is significant, is a sign of significant large-scale order on the sun. Right? in spite of all this turbulence in the interior, we've got a large amount of order here to deal with. And I like to think of it as order from chaos. So far, we just talked about the brightness of sunspots. Now I want to talk about the actual, aside from one thing, which was the original Hale measurement of the polarity. We are going to have to look at spectropolarimetry later today. And so what I want to show you here is just the relationship between what is a sunspot and what we believe is the line of sight component of the magnetic field. So if I have a vector field in that direction, only the cos theta part is measured by this particular kind of measurement when you use only circular polarization. To recover the full vector magnetic field in three-dimensional space, you have to get at the linear polarization as well. Okay, this will make sense later, I hope. Now, what this is showing you, this is a ground-based magnetogram, just at random. The sunspot appears like that, and now we see the sunspot appears like this. So this is a region of enhanced magnetic field, surrounded by stuff of different polarity, same leading polarity here. But we see a lot more stuff here. This is the same day, so we don't hardly see anything here, and yet there's a lot of magnetic flux here. So in other words, magnetic signatures are present, but there's a distribution. Only the strongest and most densely packed fields, large enough, show up as a sunspot. So that we're looking at a sort of tail of a distribution again there. The rest of this stuff is perhaps a bigger part of the distribution of the magnetic fields on the sun. Okay, that's just for a definition here. Now, I wanted to play you this movie, and this is one that was chosen by Hank Sprout in his Hale lecture. So what this is again, the line of sight magnetic field. White is pointing towards us, dark is pointing away from us. This had the name the trilobite because of this guy here, which looks more like biology than it does physics. But what I want to draw your attention to is, if we look in very fine detail and on fine time scales, this is with the Hinode spacecraft. Space is a wonderful place to be if you want to just sit and stare at something for a long time, right? I mean, this is hard to do from the ground. You can do it, but you have to coordinate observatories and different observing conditions. Okay, so this is one of the real advantages. This is almost, many of you will know what fractals are, probably much more than I do, because they're much more. This is almost a fractal-like structure. As you magnify in, you find more and more of this structure that looks rather similar, and that's quite dissimilar from these very strongly concentrated fields in the core of the active region itself in the sunspots. Now, the other thing that's interesting here is, as we see this is separating out polarities here. And one of the things that Hank Sprout points out is that by separating out polarities like that, this is quite the opposite of a diffusive process. There's some real large-scale dynamics going on that's forcing this system. What it is it's flux emerging from beneath. And we're seeing the projection through a plane of this three-dimensional magnetic field emerging through the surface of the sun as a result of observing this kind of thing. Now, the reason he points out that this is kind of looks like the opposite of diffusion, I mean, you're separating polarities here. This is moving away. This stuff here is moving that way. And you can imagine that quite simply by having the elephant's trunk poke through the surface, and then you see stuff separate as it's rising through the surface. That's a big, large-scale dynamic event driven by magnetic forces interacting with a convective layer underneath. It's quite different from a diffusive process. So the reason that he brings that up is that in his criticism, which is one of the papers I've included in the website I pointed you to, of mean field theory of dynamos, which I'm sure Fausto will talk about tomorrow, is that there's something really missing from treating the solar dynamo which is attempting to describe this kind of behavior on a large scale, if you just treat it as a large-scale evolution of a large-scale average field plus a diffusive term. And that's one of the things I'm going to talk about on Thursday is Henk Sprout's criticisms and Gene Parker's criticisms of current dynamo theories. Basically, the diffusive picture of it generating helical turbulence by a small-scale effect, and you integrate up the induction equation for the mean field in terms of correlations between things on the small scale and the mean field itself. This is what Fausto will talk about tomorrow. That kind of picture is not at all represented by what we're looking at here. I would counter that, in fact, that model isn't attempting to account for this here. It's attempting to account for a overall magnetic structure, and that there is an additional process going on which is going to squeeze these fields together and make them appear so intense and appear as spots. But the problem with that interpretation is that the spots do seem to be the prime signature of the large-scale dynamo. Therefore, I think Henk Sprout has a point in saying, and I recommend you read the paper that I put on the website there, that there is a serious problem with interpreting, with the 40 years worth of work that's gone on, integrating up a mean field in terms of the correlation functions on a small scale. Okay. Hopefully that will make more sense tomorrow. Let's take another look. This is a plot made by Karen Harvey originally. Karen unfortunately passed away about 10 or 15 years ago. She was a very talented observer, very wise, and she spent a lot of her time measuring these line-of-sight magnetic fields from the ground, which is a difficult proposition. We get used to seeing them from space, and you take them for granted. Oh, SDO's observing now. MDI's been observing since you guys arrived. You know, it's easy. This stuff it's trivial. It's all there. It's like having access to the internet all the time. That wasn't the case for many years. And what Karen did was to not only look at the spots. Remember, we looked at the spots, but now we're looking at the line-of-sight magnetograms, and she pushed it really hard. The pole of the sun, actually, the rotation axis of the sun, is inclined at about 7 degrees to the plane of the orbit of the Earth. So that sometimes we see a little bit of the South Pole, and then 6 months later, we see a little bit of the North Pole. And that tilt is sufficient for us to measure some magnetic fields here. And I want to point out something very interesting. You can see wave-like motions here, propagation here. Whenever we see a slope in a time-distance plot, so what we have is time and distance. So let's have a look, see what's happening here. Here we start up, and there's nothing much going on at low latitudes. The sunspots haven't emerged yet. They start to appear around here. Well, there's something left over from previous times as its opposite polarity here. I'm colorblind, but I think that's yellow, isn't it? Or is it green? Okay, thanks. And this is blue. So this yellow stuff in here, right, is all plus towards us, and this blue stuff here is all the way. Let's focus on this. Here is the emerging sunspots, and these appear in pairs, so you should end up with a blue and yellow right next to it. They're not resolved on this plot, so what you're probably seeing here is the dominant polarity of the leading spot, because the other ones are dispersed. But so what you're seeing is this stuff is gradually, it's emerging and going towards the equator as the solar cycle progresses, and basically disappears here. And then the opposite polarity starts to dominate here, and the same thing. So here's the solar cycle and the sunspots reflected in the magnetogram. But look at this stuff. We've got stuff going this way. So this is a propagating phenomenon from high latitude to low. This is some clue as to the deep-seated root interior of the sun about the dynamo. And right here, we've got stuff that's propagating towards the poles here. What is this? The sun, like all rotating bodies, fluids, has the capability of generating large-scale circulation. The Earth undergoes various kinds of circulation in the atmosphere and in the oceans, driven by various pressure gradients, forces, whatever they are. And they don't need to be very big, and they don't need to be very significant. But something like, for instance, the North Atlantic drift takes is a current that takes warm water from Mexico to Britain where it rains a lot. And, you know, so people like me have webbed feet and, you know, you sort of have, never mind that. But anyway, that kind of current, it's not very fast. It's not a speedboat, but it's this damn thing that just keeps going and going and going and going, and you can't stop it. And if you put a little cork in there, it'll float all the way across the Atlantic eventually, in spite of all the high-frequency waves and turbulence. It'll finally get to the beach in Brighton or somewhere like that. Well, this is sort of what's going on here. Magnetic flux is being moving off towards these poles of opposite polarity. So the leading spot is here, and as I said, tilt has the following polarity at higher latitudes, which means that the blue stuff emerges here and the yellow stuff emerges slightly below it. And then as the diffusion starts to take over, if you believe the diffusive model, and with a little bit of what is called meridional circulation that moves very slowly, we're talking tens of meters a second. You guys can run that fast, no problem. And it would take you about 11 years to walk from here to here. What's going on is that we've got this system now where flux is emerging, it's tilted, it's diffusing. Because this stuff is the opposite polarity to the stuff emerging here, it makes it to the pole, and once enough of it makes it down to the pole, the idea is that some magic reconnection happens at the surface, and we flip the polarity. So now let's look at this thing from the point of view of what is the dipolar field doing. Let's project this onto a dipole. Well, pretty much this stuff is going to cancel out. That's a high-order multipole on the scale of the sun. But this stuff here is not. Here is a positive polarity. Here's a negative. So if we only look at these things and this one, we're looking at the top and bottom of we're looking at the field lines coming out of the top of the pole and the bottom of the other pole. We see it changing sign every 11 years. So this is a really fundamental property that Karen Harvey found out about the sun. And these phenomena here are called rushes to the pole, if you've ever... And that comes from the history of the race of Scott of the Antarctic against Amundsen, where there was a rush to the pole. And Amundsen, I think, kind of cheated and ran to the pole ahead of Scott. The rush to the pole that's going on here, though, takes a few years, and it's more of a crawl, but it's significant. And in fact, if one continues the idea that one's got a meridional circulation, then that circulating material is going to pile up unless it goes somewhere. Where's it going to go? Does it squirt out the top of the poles? No. It tends to go back down again. And if you include the idea that you have large cell convection, large cell circulation, then the idea is that some of this flux gets dragged down into the sun, into the core of the sun, where it can change the magnetic field in the interior to the opposite sign to what it was before. Let's look at it from another point of view. Here, we have primarily a toroidal field. It's in a rope shape, because what's going on is the field emerges at the surface, comes up, and it's a little bit tilted, but it is mostly a ring of field at a constant latitude, which then pokes its head up and is aligned in the east-west direction. This, on the other hand, is a poloidal component. If we start from a sun which had a dipole in it, so we put a big orange here and we just put a dipole field through it, the differential rotation I showed you earlier in the sun is capable, remember the induction equation, partial d by dt plus v dot grad of b equals a stretching term plus a compression term. Let's forget the compression term and look at the stretching. We have differential rotation somewhere in the interior. Say we have latitudinal differential rotation, so it's rotating faster at the equator than it is at the poles, which is what's going on. I put a bit of magnetic field in there. I'm starting to stretch the field line. And these field lines that were originally like that, they start to go like this. And after a little bit of time, they get dragged all the way around until they become, you convert it from a poloidal field into a completely toroidal field. And with a little bit of reconnection, you can make the entire interior of the sun a rope. So the idea is that what we're looking at here is the emergence of ropes generated by differential rotation in the solar interior somewhere. And those regions of the sun where that happens were in that plot I showed earlier, which showed you the differential rotation from the Brown and Morrow paper in 1987. There are two regions, there are basically three regions of differential rotation that helioseismology has discovered. One is just above the, right at the interaction zone between the core and the convection zone. That has components which are in the radial direction and in the latitudinal direction, r and theta. The other one is right at the very surface of the sun. So there's some slippage at the very surface. Those are ideal places for us to generate magnetic field as a result of stretching from the induction equation if we know how to do it. That's the easy part of the dynamo. The really tricky part is to take this toroidal component, which is a ring, and convert it back into the poloidal component. And there are various, there's a lot of history involved in doing that. If we believe that differential rotation is the thing that drives the sun to produce sunspots, because it's compatible with this kind of observational data that we have, then the only thing we've got to do, remember the sun is a cycling thing. If we convert poloidal field, dipolar-like fields, poking out of the north and south poles of the sun into a east-west oriented azimuthal field, toroidal field, we've got to do the reverse. We've got to take that one and convert it back into something going the other direction every 11 years. That is the key to the dynamo problem, solving the dynamo problem. That mechanism. I believe we know what the interior processes are that generate the toroidal component. It's the other one. And they have words like alpha effect. And the reason for that will become clear from Fausto's lectures tomorrow. Do we have a break for a bit at some point? We could. Let me continue here. I want to show you this wonderful movie made by David Hathaway. What this is again, line of sight magnetic field. And as time goes on, you can see the solar cycle varying. The way this is built is you basically take the sun's disk and you take the central part and you measure what's there on one day, and then you stack it up for the next day, and you stack it up the next day, and you make a long thing like this. So what this shows you is, instead of a static picture like we had there, this is actually showing you the motions of various features when they're averaged, or at least sampled, by the meridian of the sun. It's like looking only at the Greenwich meridian at noon on the Earth and asking what's there. That's what they're doing. And then they make a movie out of this thing. So here you can see this is very strong magnetic field. So look at those blue patches at the top. Regions of unipolar field surviving for quite a long time. And this bit now is, so that's one time. And now, as time goes on, you see the solar cycle and stuff moving backwards as the rotation is slower. This has to be synced according to the rotation rate. And things that appear to go backwards, they're just rotating a little bit more slowly. The sun does not rotate uniformly, so they appear to go backwards. But actually what's going on, stuff is propagating towards the poles there. So it's like looking at what you do is if you took a picture of the Earth from the sun, and you looked at the Greenwich meridian every day, and you asked what's there, you'd find, the North Pole up here. You find Scotland, England, and some of France and Spain, and you make a plot of that, of what's there on that day. Then you put that to one side and look the next day, and then you see what's there the next day. Well, you're only going to get bands, because it never changes on the Earth like that. You might see some changes in snowfall. You might see some weather patterns on there. The same thing is being done here. at noon every day you take a picture and you stack them up side by side. The problem is that the sun is rotating more rapidly at the equator, so stuff can appear to go backwards in time because they're not able to catch up quite. So that differential rotation hasn't been taken out. I believe that's the case. Does anybody actually know? No solar physicists here. Pardon? Yeah. Okay. So sunspots are part of the story. We see surface effects. We know that there is meridional circulation. You can actually measure patterns on the sun and watch them move towards the poles. We don't know how deep those go, so we don't know how they're connected to any interior induction equation to make the dynamo work. That's a big question right now. But certainly, this is a turbulent-looking thing at the surface of the sun. Here is the much stronger field, which is less turbulent, as you'd expect. Okay, let's continue here. So my interpretation of this is that we are getting it's a chaotic system, but there's a lot of order in it. Or you could say it's the ordered system with a lot of chaos in it. So it's kind of the worst of both worlds in some sense, because you're tempted to try and model it as a strict clock, but then it's not. And so, it's not a tricky thing. But it's not unexpected. I mean, look at those equations of motion. The one thing that Fausto hasn't mentioned yet is he's spoken almost exclusively about the induction equation, which is, as he said, is a linear equation. d dt of B equals curl of V cross B plus eta del squared B. It's linear if you only prescribe the velocity. On the other hand, we know the equation of motion itself of the plasma, the bulk equation of motion of the plasma, consists of the rate of change of momentum equals the sum of the forces on it. One of those forces is J cross B. J is curl B. It's a highly nonlinear term. So by focusing on the induction equation, he's forcing you to think, which is perfectly fine, forcing you to think kinematically. We prescribe the velocity field and ask the question, how does the magnetic field respond? That's a linear problem. However, what we've really got is a system of equations. We've got a continuity equation, we've got a momentum equation, we have an energy equation, and then we have the induction equation. If we look at those equations, we see that the things we've got to solve for are the density, the temperature, so we need an equation of state as well, the velocity of the plasma, and the magnetic field. So we've got a system of equations which itself is now nonlinear. So by separating out the induction equation by itself is a great way to learn about the growth of magnetic fields from zero. But there will come a time when you have to worry about the J cross B force affecting V, and thereby that messing up the V cross B that your assumed induction equation was linear in. So I'll get to that as well. Another thing is that the active regions tend to pop up in groups. If you've ever had a sports injury, you know that you're likely to injure the damn thing again. I have one where I was running for a train in Oslo, and I thought somebody had shot me in the leg, and I still have a nasty, this is 30 years ago, and I still have a thing. The sun seems to do the same thing. It tends to emerge spots at the same kind of longitude over unreasonably long lengths of time. With run rotation takes about a month of our time, and these spots can go on for several rotations. This is an example, 15 rotations. This is almost a year and a half of data, and yet what you're seeing here is places where these things recur, and these things don't live that long. These are not the same spots. It's like having a hernia. The sun somehow remembers that it's, stomach's going to fall out of here, and then another one's going to fall out. It's like, for God's sake, the surgeon hasn't fixed me up properly. This is still happening. Please fix it. A very curious thing. In amongst all that noise, you can make one critical measurement of a very, very different kind. That measurement doesn't depend on the direction of the magnetic field. It depends only on the strength of it. And we'll get to it later, but it's called the Hanley effect. I mean, we have to use any tricks that we can to get at the magnetic field of the sun because, it's so important in so many ways. But this is one way we can do it. And what this is a plot of is the first plot that I know of, Lucia Klein, where she was working on a thesis in this period, so you can see many more measurements, and odd people did these measurements. These are very, very difficult measurements to make. Incredibly sensitive, well-calibrated instruments are required to make these kind of Hanley effect measurements. Absolutely no relation to the sunspots. This is a measurement of the quiet sun at some high latitude and medium latitude and average in some sense. And apparently the quiet sun magnetic fields don't know anything at all about what's going on globally. That presents us with something of a puzzle if we really believe about spots emerging and diffusing across the surface, because that diffusion has got to come with some flux which should show up here in various parts of the sun which she is directly measuring, but it hasn't shown up here. There appears to be something about the sun that is robust against the solar cycle in the overall average magnetism of the sun. So when one looks at nauseating detail, one finds sheets of material, blobs of material which are magnetic. One finds various situations here in amongst all the chaos. Let's take a break for... Can we take a break 5 minutes? I need a drink of water or something. That would be great. If we could, that would be great. Thank you.